In 8.1, we're going to take a look at the distribution of the sample mean. So what we're talking about here is rather than looking at the distribution of the actual data set itself, the actual population, we're going to be looking at, as this sampling distribution describes, the distribution of all possible values of a statistic from a sample size of a certain size n. And so specifically right now in this section, we're looking at the sampling distribution of sample means. The idea is we want to think about every single possible sample mean that could come from a sample of a certain size from a given population. So why is this important? Well, it's important because it allows us to kind of extend the processes we learned in Chapter 7 to answer an entirely different set of questions. In Chapter 7, we focused on this question. I even kind of emphasized this phrasing: the probability that a randomly selected, and then whatever the topic is, in this case, randomly selected American watched more than 9 hours of TV in a week. If that was my question, it's a question we could have seen in Chapter 7. So in Chapter 8, we can extend this style of question to what's the probability that if we took a sample of size, in this case 10, that the average number of hours watched was more than 9. So notice it's the same, content of question, but the subject matter is different. Rather than looking at one individual out of a population, we're asking for the chance that if we took a certain sample, what the sample average or sample mean would be, and what's the probability that sample mean would be more than 9 hours. And that is definitely a different question than one from Chapter 7. So the difference: in Chapter 7, we looked at a data value. In Chapter 8, we'll be looking at a sample mean. Now, a little more about what that means for us. This is just kind of a setup to try to understand the situation, not so much specifically a question you've got to really deal with in this chapter, but just to further understand what's going on. We're going to start with a very simple, very small population of a student's scores. We're going to say there's 5 students, and these are their scores in a specific class. There's their average, there's their standard deviation, right? What describes the spread of that data. So a population of only 5 is not a big population, but if we were to consider every single possible combination of 3 of those values, now we're going to even consider the ones that don't make sense in that we'll say 75, 75, 75. We're basically saying a sample with replacement. So you could get all 3 of the lowest value there, 75, or all 3 of the highest, 92, or any other collection of any 3 numbers from this set, with repetition allowed. And so what happens is you take those numbers and you look at the sample mean created from each of those samples. Well, considering what a sample mean has to do, it has to take the average of 3 numbers. So aside from what you could call the extremes of all 3 of your lowest number giving you a sample mean of 75, or all 3 of your highest number giving you a sample mean of 92, most of your sample means will include numbers, some from the low and some from the middle, or some from the high and some from the middle, or all from the middle. Or what we're going to see with this, just by running through a couple of the examples, is you get sample means that are closer together, right? You get the upper 70s, you get the low 80s especially, right, when you're taking 3 of these numbers. So what happens is that data set, first of all, it's much bigger. Notice we only have 5 numbers in our population, but there's a lot of different samples of size 3 that can be taken. So you get a larger data set, but specifically that larger set of numbers is less varied. It's less spread out. You have far more numbers in the center, and only that one extremely low number of 75, or that one from the 92, 92, 92, extremely high value of 92. So in comparison, the standard deviation of this set of numbers is going to be smaller. Now, I didn't write out every single pair, but here I have what would have been the sample mean and the standard deviation, or the mean and standard deviation of the sample means. So again, if we used these numbers as our data set, the mean of those numbers, well, that's going to be 77.6, which is the same exact mean of the original population. But the standard deviation of our population was a 9.48, describing the spread of those 5 numbers. The spread of the numbers we get from the sample means, if you calculate it, is actually a 3.93, much smaller. So what happened to the mean? It remained the same, right? The mean did not change at all. But the standard deviation, it was reduced, right? That 3.93 is a much smaller standard deviation than this 9.48. These values got kind of pulled together, right? You've still got the few extremes, but you've got more and more and more in the center of your data set. And so that leads to a smaller spread, a smaller standard deviation, okay? So with that in mind, taking a look at this example again, or not this example rather, but another example, looking at an example of the weights of pennies minted after 1982. And so we're going to say that this set of data is known to be normally distributed with a mean of 2.46, standard deviation of 0.02. Okay, so again, that's our actual data set. But then let's talk about taking samples of size 5 from that population. So now, again, our population's huge. We don't even have a number for it. But our samples that we're taking are size 5 this time. And so taking a sample of size 5, here's one sample, one collection of numbers, and it's got a mean of 2.479, right? And so what if we took 200 samples of size 5? Okay. Well, here's a distribution of what 200 random samples from this population could look like, right? And what we want to notice is, basically we're telling you that this data set has a standard deviation of only 0.0086. Okay, now that's definitely a lot smaller than that 0.02 that we saw before. Now, what if instead we leave it as 200 samples, but if we increase the number, the size of our sample size from 5 to 20, okay? So increasing the sample size from 5 to 20, but keeping the same number of samples gives us this distribution, which if you compare the two, we would say that both look relatively bell-shaped, but this one looks more symmetric, right? This one's got a bit higher peak and a little bit more variation going on as you compare left to right of center. This one, again, there's still some variation because 200 isn't a huge sample size, a set of samples, but notice it's definitely a more uniform bell-shaped distribution going out there from the middle there. And so we see also the standard deviation drops even more. So increasing the sample size also is a way to decrease the standard deviation of your distribution of sample means. So both the size of your sample and the number of samples we've seen are going to change the standard deviation for your sampling distribution. Now, to look at exactly how much it changes and how it changes, we've got these two formulas, or actually three. So these two individually are the ones that tell us that the mean of our sample means is still the same as the original population mean. Okay, that's that symbology there. The mean of our sample means, or the mean of the distribution of sample means, is nothing more than the original mean. But the standard deviation of sample means, that's what changes. And it changes by the original standard deviation of the population divided by the square root of the size of your sample. Okay, that's what n represents, how big of samples you're taking. Now, those two individual formulas are good. Where they really come into play for us will be in a revised z-score formula. Recall the original idea of a z-score is its value minus the mean over the standard deviation, right? That's our overall understanding of a z-score. Well, our values, when we're talking about a sampling distribution of sample means, are the value of an x bar. The question we're going to see here in a moment will be about the sample mean. The mean of the sample means we just saw is actually the same as the original. That's why we don't need anything different. We can still use mu right there, just like we did in the original z-score formula when it was x minus mu over sigma. But then the standard deviation we saw does change. So the standard deviation here in the denominator is that sigma over square root of n formula. So this right here, very important formula that we're going to need for these questions that involve the sample mean. So let's take a look at this first question here. So we're back to the pennies. Right now for the moment, we do have that our distribution of our original data set is normally distributed. That means that any sample that you take is going to have a roughly or approximately normal distribution as well. Okay, so that's good to see. And then we have the mean of 2.46. I'll just kind of label these things. The mean is 2.46. Standard deviation is 0.02. What's the probability that a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? All right, so we're taking a sample of 10, right? That right there tells us our sample size, n. And we want it to be at least 2.465. Now here's where chapter 8 and chapter 7 look a whole lot alike. This question of finding the probability will look just like our question from chapter 7 of finding the probability. Just tiny differences. That very first picture we draw, if you remember I used to call it data world and label it with an X, well, now I label it with an X bar because this distribution, the one we're concerned about because of this question, isn't about the original data set of pennies, it's about the sample means that came from samples of size 10. So again, this is like the entire distribution of every possible sample mean from 10 pennies and their weights and their sample average. That's what this represents. Now, we know that since the original mean was 2.46, that this data set is also centered at 2.46. So 2.465 is slightly bigger. It's somewhere to the right of center. So 2.465. And we want the sample mean to be at least this. At least that means that or more. So we're interested in the shaded region to its right. So there's our original, what I normally would call data world, or in this case, it's in the sample means world. And we want to then convert that, like we're doing in chapter 7, to a z-score world picture, which will have the same placement of a line, same shaded region. But to figure out that z-score, here's where we will use our revised z-score formula from up above, because we're dealing with a question about sample means. So our revised z-score formula looks like that. And so our sample mean value is the one in question, 2.465. The population mean value is the one we were given in the problem of 2.46. Standard deviation of 0.02 and the sample size of 10 in there. So this is another one where you want to be careful as you're entering your numbers. Make sure your calculator knows what you're typing. So I'm going to use parentheses to do 2.465 minus 2.46. Close those parentheses, then divide it by, and just, oops, wrong button. Divide it by, and just to be safe, just for organization, I'm going to use parentheses again. 0.02 divided by the square root of 10. 10. Close the parentheses on the square root, close parentheses on the denominator of my fraction, and that will give me my value there. No, it will not, because I mistyped something. Ah, there it is. All right, I'm going to use second and enter to bring that back up. Go up here and enter a 2 to have that correct. And that should be 2.46. And now, there, that looks much more like a possible z-score. So we're getting 0.791 if I take my z-score to 3 places. And so 0.791, remember, very important, this is a z-score. This is not the probability, even though that decimal looks like it could represent a probability. It is labeling the location of that line. That's what we're getting from a z-score formula. Once you've labeled the picture, now we can use this z-score in our normal CDF function and say we want the area from 0.791 off to some big number like 10 or 100. And that value coming out to 0.2145 if I round it to 4 places. That represents the area under the curve, which represents the probability we're looking for. So we can then answer this question. The probability a sample of 10 pennies minted after 1982. Probably a sample has a mean weight of at least 2.465 grams is 0.2 1, 4, 5. So again, we're really just rephrasing this question, the original question. Things I like to see in there, you want to understand that you're taking a sample mean, or a sample of a certain size, and that you're saying the mean weight, right? Because it's a sample, so the sample doesn't have a weight, right? That's 10 different pennies have 10 different weights, but what the sample has is a mean weight. And then in this case, that's what we were looking for, and there's our probability.